Let us now solve question number 17. It says a point mass M is suspended at the end of a massless wire of length L in area cross section A. So this is a massless wire. There is a point mass of value is small l. In symbols only they are given. Length is L. Area, this area, whatever area, small area to have, area cross section is A. Young's modulus of this wire is given Y. And they want you to find frequency of simple harmonic motion along the vertical line. So since they have given to you Young's modulus, it means this wire is not an ideal wire, which we assume in the beginning of first PU when we do laws of motion, where the wires are inextensible. Here the wire has Young's modulus. So this wire will act like a spring, whose spring constant, if you remember the formula, is YA by L. So if you have forgotten, let me just quickly revise. For a spring, you know the spring force we write Kx in magnitude, right? Where K is the spring constant, X is the displacement from its natural length. Now for a wire, the Young's modulus is defined as stress, which is restoring force per unit area, divided by strain. Strain is change in length by original length. So force will be what? Cross multiply YA delta L by L. So delta L is what? The change in length, which means the extension from its natural length, right? So this is your X, right? So this K must play the role of YA by L. So this wire will basically act like a spring, whose spring constant is this much, and you have suspended this particle here, M. So the time period of oscillation will be same as for the spring block system, which is very simple, 2 pi root over m by k, and k is what? YA by L. So that would be the answer. So this means the answer is 2 pi. So they want frequency. So this will be 1 by 2 pi root over YA by ML. YA by ML. So this is option D. Okay. Next problem, question number 18, is also based on finding the period of oscillation for another kind of system. So if you are given a rigid body, then there is no concept of finding period, because that body will not change its dimension, so there's no question of coming back and performing oscillations, right? But now in 18C, what they are asking, a rigid cubical block A of mass n and side L is fixed rigidly on another cubical block of same dimension and of same modulus of rigidity eta, such that the lower face A completely covers the upper face of block B. So here is a block, cubical block A. The mass of the cubical block is m, length of the cubical block is L, onto another cubical block of the same dimension, and modulus of rigidity for another block is eta, such that lower face of A, so this lower face, covers the upper face of B. So same block, this is B. Okay, the lower face. The lower face of B is rigidly held on the horizontal surface. So this is rigidly held on the horizontal surface. A small force F is applied perpendicular to one of the side faces of A. Side faces. Okay. So if this is the side, it is applied like this, perpendicular to this side. F. After the force is withdrawn, A executes small oscillations with time period how much? Okay. So here they are talking about shear modulus. Okay, because eta is mentioned. So eta is a shear modulus. So start with the definition of eta. So eta is force, right? Stress by strain. Strain in this case is what? Theta. Theta is what? So what will happen is this whole thing will twist by some angle theta, right? So if the displacement caused here is x and side is L, then for small displacement this theta can be written as x by L. This theta can be written as x by L. So what will be your force? Eta A x by L, right? So now what will be the acceleration? Will be the force. When you remove this force, the same restoring force was acting on the body, right? So when you remove it, the body will come back, and the x force will be eta A by L divided by mass of the body is capital M into x. So this quantity will play the role of omega square. So period will be what? 2 pi divided by omega. This is your omega square. So root of this will be omega, so the root over ulta it will become, right? Lm by eta. So here area you can write as L square. So one L will cancel. So it will be 2 pi root over m by eta L, m by eta L, option D. So you can think of this as some jelly, right? So if you take a jelly and you apply a tangential force parallel to its surface and then you leave, it will vibrate, it will oscillate. And the period they are asked. Let's see question number 19 now. So it says a thin metallic disc with mass 2 into 10 power minus 2 kg and radius 2 centimeter is attached at its center to a long fiber. So let me draw a diagram. Okay, this is question number 19. So there is a disc and mass of the disc is given to be 2 into 10 power minus 3 kg, actually not 2 kg, and radius of the disc is given 2 centimeter. This is attached at its center to a long fiber. Okay, so this is a long fiber. The disc, when twisted and released, oscillates with a period of 1 second. They want you to find torsion constant of the fiber. So let's say C. So this is your torsion constant. This quantity in first PU we have seen in gravitation chapter when we try to find gravitation constant using Cavendish experiment. Okay. So what happens is, let us try to understand what is this torsion constant. See, if you take a spring and if you displace it by x, then there is a restoring force, and if you assume it obeys Hooke's law, then this force will be proportional to displacement. The constant will write k magnitude. The minus sign says the force is opposite to displacement. Similarly, if you take a wire, okay, let me show you slightly bigger, and if you twist it, okay, twist it means what? Keep one end fixed, hold the other end, and you turn it. So by a slight angle, this wire has been twisted as phi, let's say. Then you know that if you leave it, it tries to come back. So there will be a restoring torque. So if you follow the analogy, the role of force will be played by torque. The role of linear displacement will be played by angular displacement. So this force constant is now called torsion constant. Okay. So there will be a torque developed in this problem which will be equal to C times phi. Okay, and that torque must be equal to, now Newton's second law for rotation chapter, how do we write? Torque equals to I into alpha. Right? This will play the role of mass, this will play the role of acceleration, which is called angular acceleration. So what is the angular acceleration? C phi by I. Minus sign would just mean that, you know, if your displacement, angular distance clockwise, torque will be anti-clockwise because it is a restoring torque, right? So you can put a minus sign. So that means this quantity must be your omega square. Okay, so omega for this disk will be root over C by I. So time period is mentioned, so omega will be, you know, 2 pi by t C by I root. So you are supposed to find torsion constant, so square both sides, become 4 pi square by t square into I plus multiply with C. and this disc will rotate this way, right? So its moment of inertia about an axis passing through its center and perpendicular to its plane is how much? mr squared by 2. So you can do the substitution and get the answer. Okay, let me see what options they given. Sometimes they give in terms of pi, so there's no point. Yeah, it is in terms of pi, so it becomes easy now. So keep this pi as it is, pi square as it is, substitute the value of mass and radius, you will get one option as the right one. Okay, let's see the next question. It's a very interesting question. So for spring block system, you know that the time period of a spring block system is 2 pi root over m by k. That is true when your block is attached, horizontally to a spring, and then you stretch it and you leave it, it oscillates. In fact, even when it is made to oscillate vertically, the period of oscillation remains the same. So to understand that, see here when you don't connect the block, this is the natural length. Now you put the block, that itself will be the length. It's not going to stretch by itself, right? So this position, the natural length position, matches with your equilibrium length, or the length which the spring has in equilibrium, because there is no force which is trying to pull it this way or that. It's only when you displace it by some distance x, then there is a extension and there is a force which brings it back. Vertically when you do, see what happens. Right now no blocks are connected, so this is your natural length. Okay. Now when you connect the block, it will come here. Now this extension, let's say, is equilibrium extension. This is where it stays in equilibrium. So this is equilibrium length. That means your mg is balanced by your spring force kx0. So x0 will be what? mg by k initially. Now if you want this block to oscillate, you have to displace it from its equilibrium, which we write as x. Right? In SHM, we are displacing the body from its equilibrium position. So now your equilibrium position is not this. Okay, so this is this. So you have to further displace it by x. So what will happen now? The extension has increased. How much? It has become now x plus x naught. So spring force will become more. Before, spring force was balancing mg, right? Now spring force will become more. So the net force will be what? The spring force is k x naught plus x. This is the full extension now, minus mg, and this force acts in a direction opposite to your displacement, so you can put a minus sign. Now if you see carefully, this kx0 minus mg will cancel, because kx0 is equal to mg. So kx0 will cancel mg, you are left with kx, right? So the acceleration of this block will be force by mass, so minus k by m times x, and this will be your omega square. So omega will be now root over k by m. Same as here also omega is root over k by m. So in what orientation you keep the spring, it doesn't matter. The oscillation will always have an angular frequency of root over k by m. So while finding angular frequency or period of oscillation, you should only worry about the extra extension, not worry about the initial extension which was balancing mg. So just displace it further from mean position, then that will bring an additional spring force, and that itself will be your restoring force. So no need to write this step again and again. Okay. So based on this, the next question is asked, which is question number it's question number 20. Okay. So they have given you a different kind of system. So here there is a spring, there is a pulley, this is fixed, and here there is a block. So they want you to find the time period of this system. So for this, some few things you should remember. So if the pulley is ideal, which means massless, then if tension here and tension here is T, and tension here must be in this part of the string, if there is any string, will be 2T. That is because if this pulley is massless, then net force will be MA, but M is 0, so net force will be 0. That means if here tension is T and here T, here it must be 2T to keep the net force 0, even if the pulley is accelerating. Okay, so that's the beauty of mathematics. Right? When you write F equal to MA, it means what? It means if this is 0, this need not be 0, but still this will be 0. Meaning, if the object is massless, if you are assuming, then it means even if net force is 0, the body can still have acceleration. So here in this problem, the pulley is ideal. Okay, that means the mass of the pulley is very small compared to the mass of the block, so you can neglect it. Another thing you have to understand is constant relations, and that is if you have a pulley and here you have strings connected. If this end has displacement x1, this end has displacement x2, and this end has displacement x, then this will be always equal to mean of the displacement of the two ends, x1 plus x2 by 2. Okay, so these things we study in laws of motion. This is oscillation chapter, so we will not be discussing in detail about this. If you have forgotten about this, let me know, I will revise this also. So here how to solve this problem. See, we want to find which is the net force which brings it back once you displace it from mean position. So imagine the system is right now sitting in equilibrium. Okay. So if I give it a displacement x here, okay, then there will be an increase in the tension here which will bring it back. So let us say that increase in the tension is T itself. Now this string is ideal, so it is T here, this will be also T. Right? So here it must be 2T, which I mentioned before. Now here if the displacement is x, this end is fixed, right? So this end will have 0 displacement. So this end will have a displacement which is according to the pulley formula which I wrote. The mid end of the pulley will have a displacement which is average of displacement of this end and that end. So it will be 0 plus x by 2, which will be how much? X by 2 expression. So this 2T is what now? The 2T is the increase in the spring force here. So 2T must be equal to your K times X. And what is X for the spring? X dash, which is how much? X by 2. So T comes out how much? K by 4X. And you know that this block was displaced from its mean position by X. And the additional tension which brings it back is T. I'm not worried about mg and the initial tension. I know those two were balancing each other before, right? So this is the tension which brings the body back. So on this block, the tension is T, which is the net force which brings it back. And what was the rule? The rule was to write that force as some constant into x, so that your acceleration will be force divided by mass, and the constant by mass will be your omega square, right? So here we have done that already, right? So this k by 4 is that constant. So now we have to find acceleration of this mass. That will be the force on this mass, which is T, not 2T, okay, mind you. So tension by mass, so it will be k by 4 m into x. So this will be your omega square. So omega will be root over k by 4m. Time period will be 2 pi by omega, so root over 4m by k. Right?